So, welcome everyone. I would like to express my gratitude to all those who have joined us today. My name is Haoran Kim, and I'm from the University of Melbourne. I was one of the ICANX Young Scientist Award winner in 2019. I would also like to extend my special thanks to Professor Haisha Chang, the host of the ICANX webinar series. It is my great pleasure to introduce three outstanding young researchers in the field of nanophotonics today. Our first speaker is Inki Kim from Sungkyunkwan University, followed by Mengjie Yu from University of Southern California, and lastly, Haoran Ren from Monash University. There will be no breaks between the three talks, and we will proceed to the panel discussion session after the third speaker's presentation. You may submit your questions at any time, and we will address them during the discussion session. So without further ado, let me introduce our first speaker. Inki Kim is an assistant professor in the Department of Biophysics, Institute of Quantum Biophysics at Sungkyunkwan University. Today, he will be talking about metasurface-enhanced holography, imaging, and biosensing. Please welcome our first speaker, and Ingi, the stage is all yours.
Okay, thank you. And wait a second. Can you see my screen? Yeah.
Yes.
All right. So thank you very much, Professor Sejong Kim. It's my greatest pleasure to be here. My name is Inki Kim. So today I'd like to share my research on metaphotonics for flat optics. So here I'd like to share three examples: holographic displays, active metaphotonics, and imaging technologies. All right, this is the story where we begin. So the metasurface-based flat optics, it is well known new types of optics area. So as you know, the conventional optics, it is based on refraction and diffraction. As you can see here, the camera lenses and AR real display, all of them are ruled by refraction and diffraction. But the disadvantages of refractive optics, you always need a certain volume to accumulate phase. So you always have bulky system. And also for the diffractive optics, their optical performance is limited by geometric parameters of optical components. For instance, periodicity of grating, the viewing angle is limited. But here, the metasurface-based flat optics, it can overcome those drawbacks. By implementing functional nanostructures, we can not only shrink the device volume, but also we can enhance the device performance, like image resolution or viewing angle of AR rear display and so on. So to replace those conventional optical system, we are gonna adopt metasurface technology. So the most useful thing from the metasurface is actually we can control the phase or amplitude and polarization of light at the sub-wavelength region. So wavefront engineering can be realized. And here's the basic principle of metasurfaces. Let's consider we have two different medium, and let's say light is illuminated at the interface, then light will be bent according to the Snell's law. But what if there is a metasurface at the interfaces? Then light will be bent according to the generalized Snell's law. So here, according to the abrupt phase gradient term, we can realize anomalous reflection. So through this concept, actually, we are able to realize optical wavefront engineering so that we can realize lenses, hologram, and optical clocks, and so on. So I've been working on this area, metasurfaces like holograms, lenses, and observers. And also I've used functional materials like liquid crystal and active semiconductor to realize active metaphotonics. And also, I've developed several unconventional nanofabrication methods. And these days, I'm interested in practical application like a LiDAR, 3D sensor, and photonic circuit platform. First theme is ultra-compact holographic displays. So, as you know, the holography is a well-known 3D display technology which can record all information of light, like amplitude and phase. So it can reconstruct wavefront of light in the space, so you can feel a sense of volume. So in conventional way to encode hologram images, so people usually used these kind of optical setup. First, we split the beam, and one of the beam will be illuminated on the object. And by interferencing between scattered light from the object and the interference beam, we may record the interference pattern at the photoreactive film. And this photoreactive film, if we eliminate the light to the film, then we may reproduce encoded hologram. And this is the conventional way, but there is another way, which is called computer-generated hologram algorithm. So, for instance, if you want to float this target image in the space, then we may calculate the corresponding phase plate. So let's say if you have a target image and then you know that the information of amplitude, but you don't know the phase information in this time. So first you're gonna put a random phase information, and then you will do backward diffraction calculation, which is basically inverse Fourier transform. Then you may calculate phase plate information. And through this calculated result, then you will do forward diffraction calculation again. Then you will calculate discrepancy between target image and calculated result. And by the iteration, you may find optimal phase information for the hologram. So this is well-known Church-Sexton algorithm, which is well-known computer-generated hologram algorithm. So in my work, I've used this algorithm. And if you find proper phase map, then the next step is to implement nanostructure or metasurfaces to induce the phase. So there are three well-known three types of metasurfaces, like waveguide type, nanoantenna type, and wave plate type. And in most of my work, I've used wave plate type metasurfaces. And here is the basic principle. So these nanobars structure will be regarded as half-wave plate, and we are gonna shine LCP or RCP light. And then if you calculate Jones matrix from the structure, then you will notice that there is a geometric phase on the counter or cross pollution part. So this phase is actually it is proportional to the rotated angle of nanorod. And also, by changing the size of nanobar structure, you can induce additional phase called propagation phase. So these four are important parameters to induce artificial phase. And this is basic history of metahologram. So in 2013, the first metahologram were demonstrated. So at the time, a gold nanosilic structure or gold nanobar structure have been used. And a few years later, metal insulator metastructure was proposed to increase efficiency up to 80%. And later, titanium-based all-directory metahologram have been proposed. And these days, a multifunctional metahologram has been actively investigated, like angle multiplexing or polarization multiplexing metahologram. So in my work, I've been using hydrogen alpha silicon for our metasurfaces. So as you can see here, the NK curve compared to the titanium and gallium nitride, amorphous silicon has higher refractive index, and also compared to the amorphous silicon, it has low exchange coefficient, which can show high efficiency. So that's the reason why we are using hydrogenated amorphous silicon. And the first example is dual mode meta hologram. And our interest was to encode multiple information in a single device. So here we are using two different materials, hydrogen for silicon and gold. So silicon, it works for visible meta hologram, and gold works for near-infrared meta hologram. So design principle is quite straightforward. We optimized each meta surfaces, silicon meta surface and gold meta surfaces, and then we add them together. And silicon, it is optimized for visible light. So as you can see here, cross polarization efficiency has high value, but for the gold meta surfaces, it works for near infrared. And then we can see that the composite meta surface can also high cross polarization efficiency at visible and near infrared. So to check the crosstalk between two structure, so here tall structure is silicon and the short structure is gold. So here visible light is strongly interacting with silicon structure only, but for the near infrared light, it is strongly interacting with gold nanostructure. But the but here the bottleneck was fabrication process, because it is very difficult to fabricate two different material in the same plane. So here we adopt even lithography overlay process. So first we deposit multi-layer and then define a line mark and then define chrome structure to make silicon meta surfaces, and then using even overlay process we define gold meta surfaces. And this is the fabricated device. So here we are illuminating two different light source like infrared and visible light. You can see clear hologram images. And this is a real-time movie. So we are shining visible and near infrared light together, and visible hologram and near infrared card. So you can see encoded hologram pattern. Second topic is active metaphotonics with tunable materials. And there are many interesting prior art in this area, tunable metahologram. For instance, phase change materials like magnesium and GST and vanadium dioxide. And also there are advanced algorithms to make instant angle multiplexing metahologram and orbital angle momentum multiplexing metahologram and polarization multiplexing method. So, but they are very interesting, but there are several drawbacks, like a slow response in chemical reaction and limited bandwidth, and also a complex optical schematic. So our strategy was quite straightforward. So we integrate a liquid crystal below the meta surfaces. So here, the liquid crystal is well-known stimuli responsive material. So the role of LC cell, it is modulating outgoing polarization state. So by applying external stimuli, we can change the outgoing beam polarization state. And then we just merge them together. So first, we optimize the meta surfaces. For LCP light, it will generate this one hologram image, and if you shine RCP light, you will see another hologram images. So this is fabricated result. So RCP and LCP light can produce two different hologram pattern, and then we just integrate active liquid crystal cell. The first example is electrical tunable meta hologram. So by applying a proper electric bias, we can change outgoing polarization states. So as you can see in the real-time movie, by applying electric bias, you can switch hologram pattern. And also, if you introduce the other liquid crystal cell, like a heat responsive LC cell and touch responsive LC cell, then if you heat it up or cool it down, then you can change the hologram pattern. And also by just touching the device, you can change the hologram pattern. So this is the first demonstration which integrate the meta surfaces and functional liquid crystal cell. And later we did another work. This is a gas sensor. So the conventional gas sensor is quite expensive and complicated and inconvenience. So to overcome those drawbacks, we developed cost-effective, intuitive, and ultra-compact holographic gas sensor. So our goal is to make such a visual holographic alarm. So if there is no gas exposure, then you will see smiley face. But if there is a gas exposure, you will see your alarm mark. So this is compact, flexible, and a flexible holographic gas sensor. So the first, we designed gas responsive LC cell. First, we implement micro well structure. So upon the gas exposure, liquid crystal orientation will be changed. So we may change the outgoing beam polarization state. So this is fabricated gas responsive LC cell. So design principle was similar to the previous example. And then this is a real demonstration. So here we used board marker as our primary gas source. So if you close it, if you bring it close to the device, then you will see the outline mark. And if you remove it, then you will recover its initial state. So the holographic metasurface can promptly detect a volatile gas in the air, and it provides the detection information via holographic images. And one step further, we develop one-step nanocasting process. So first, we define a master stamp on the silicon wafer, and then polymer mold is used to replicate the stamp, and then titanium nanoparticle embedded UV resin was spin coated, and then we simply print it onto the PET film, and these cured composite materials work as a metasurfaces. So this is silicon master stamp, and we print it onto the PET film, and this flexible device can be attached in the glass or curved surface. So we confirm that it worked very well. So this was the demonstration of a wearable and flexible low-cost gas sensing platform. The final example of liquid crystal-based metasurfaces is security smart label. So as you know, there are well-known security sensing security platform like holograms and RFID techniques, but there are also well-known cloning method and hacking method. But if you look at those bills, then there is a photonic structure. So this is more advanced security platform. So if you look at the here the bill, it looks different color according to the viewing angle. And also in the Canadian $20 bill, there is embedded holograms. So if you shine the laser, then you will see here the encoded holograms. So inspired by these techniques, we realized metasurface-based security platform. So the device looks like a multicolored QR code, and then if you shine the laser to the device, you can project a hologram patterns, but it has specific polarization states. So we call it vectorial hologram. So it can work as a tool-level photonic security platform. And we design the metasurfaces which can work as a mini resonator and half-wave plate at the same time, because it should scatter some color, and at the same time it should work as a phase modulator. So this is complex amplitude and phase modulation. And then by grouping some of the metasurfaces, we can generate a vectorial hologram. So here each hologram pattern has distinctive polarization state. So through this single meta atom, we can control 3 different information: amplitude, phase, and polarization. So this device, if you look at the device using your naked eye, you will see a colored QR code. And if you shine the laser, then it will project a hologram pattern, but at each area, it has distinctive polarization state, so we can specifically turn off a certain hologram images. So let's see the movie, how it works. First, we are going to scan the QR code using your smartphone, and then it will give you the first password, which is a voltage information, and then you will apply voltage to the device, then you will see such a video holograms. So this will be second password. So we propose this factorial hologram for next generation one-time password devices. So this is the last example of liquid crystal-based metasurfaces. All right, so this is the summary of the second part. Then I will move to the last topic. So the so in the very first slide, I introduced metal lenses. So compared to the conventional lenses, the metal lens, it is using a functional nanostructure. So based on this nanostructure design, we can encode multiple information in the device, and also we can do something like a chromatic aberration and tunability and so on. So there are many interesting prior arts in this area, and especially you can see these achromatic metal lenses, and also so it can be used for AR VR displays. And also there are advanced nanofabrication method to make these metal lenses in large area with cost-effective manner. So nanoimprinting based method these days, like delivery lithography, have been used to fabricate large area metal lens. And also there are many interesting works in tunable metal lenses area. For instance, here mechanical tuning. So by stretching and reducing the this flexible film, you can change the focal lengths or focal points of the lens. And also by implementing phase change materials, you may change the focal points. And also liquid crystal, again, can be integrated in the metasurfaces. So here, focusing switching metal lenses have been proposed. And our goal was a bit similar, and we want to make a very focal metal lens with metasurfaces and functional liquid crystal cell. But here, our liquid crystal, it works as a polarization modulator, which was a bit similar to the previous example. So the first, we calculated the phase information for two different focal points, F1 and F2. Then you will need two different phase map. So to realize that, here we implement 8 different sized meta atoms. So it can induce propagation phase and geometric phase at the same time. So this is design methodology. So here, simply speaking, we need two different phase map. For instance, here psi r and psi l, and here we have 2 degree of freedoms, propagation phase and geometric phase. So we can calculate the required phase information for propagation phase and geometric phase. And this is the calculated result. And if we implement these nanostructure, then we can realize these very focal metal lens. So if you shine the RCP light, you will have focal plane in F2. If you shine LCP light, you will have focused point at F1. So if you put 2 different target at F1 and F2, then we can see these target, and if you change the polarization, then you will see another target. And again, here we integrate the liquid crystal again. Then simply by applying electric bias, you can focus and defocus. And also, if you put 2 different targets, then you will see one target and the other target simply by changing the voltage. So this is a real-time video. So this electrically tunable varifocal metal lens can focus and defocus imaging, and also you can see one target imaging and the other target imaging. And the final example is nanophotonic LiDAR. So there are many interesting works in this nanophotonic LiDAR. So compared to the commercially available LiDAR, like a macro scanning method or MEMS method, nanophotonic approaches can have many advantages because they don't have any moving parts, so it is quite robust, and also device volume can be reduced further. So this is a very straightforward way to how we can capture the depth information. So first we will send the pulse, and then we will record this backscattered pulse, and then you will check this traveling time. Then you can calculate the depth. So this is the time of flight method. And so to scan the beam, so there is a motorized macro scanner where the MEMS technology can be participated. But these days, this solid state LiDAR is very popular items. So here, Rumotive, a startup company, they developed kappa grading structure with liquid crystal to scan the beam without any moving part. And also 2 years ago in Samsung, they developed ITO technology metasurfaces to make solid state LiDAR. And also there are another way to extract the depths. This is basically structured light illumination method. So in iPhone 10, you can see the components of that projector. So it will shine the structured light into your face. Then based on your 3D information of your face, the structured light will be deformed. So by reverse calculation, you can calculate the 3D depth information. So inspired by this technology, we developed the metasurfaces to shine this structured light. So this is the real demonstration. So we are spreading like 10,000 dot array into the space, and then by recording this distorted pattern, we can calculate the depth information. So this is a design method. So first, we want to split the beam, and we want to cover like a 2 pi space. So here, simply merging a 2D comp function, we can split the beam in a frequency domain. And also by change some parameters like periodicity and number of metasurfaces, so we can induce many diffraction orders. Here, like a plus minus 47 orders beam can be diffracted. And from the calculation, we find out that the diffraction angle can reach to the around 82 degrees. So in total, like 160 degree area can be covered. So this is the demonstration. So if you shine the light to the metasurfaces, it can spread that array into this 2 pi spherical area. So you can see this far field diffraction pattern. So we can illuminate this dot pattern array. And then, okay, so this is depth measurement strategy. So here we put 2 cameras. So this is actually, we call it active stereo vision. And so by using trigonometry matching algorithm, point matching algorithm, we can calculate this depth information of 3D object. So this is the real experimental imaging, and this is the calculated depth information. So without any scanning, if you shine the light to the metasurfaces, and just by capturing 2 images from the camera, then you can reconstruct depth information. And also, similar to the previous example here, we implement direct nanoprinting method, and then we can also print metasurface on the curved surface. So maybe later it can be integrated with AR VR glasses. Right, so this is far field operation. And later, if it can be integrated with VXL device, then maybe like a chip scale LiDAR or 3D sensor can be implemented. All right, so this is a summary of the last part. And I think in this metasurface area, if we can come up with a very fascinating idea of low-cost scalar fabrication method or AI-based metasurface design technique and corresponding compact optical modules, can realize like really cool photonic or optical components. All right, so these are the references and these are the funding agencies. So if you're interested in some of my work, you can look at these papers. And thank you very much for your attention. And later, I'll be happy to have your question or comment. Thank you very much.
Thank you very much, Inki, for sharing your interesting result today.
Thank you.
We'll have question and answer session at the end. So moving on to our next speaker, Mengjie Yu, who is an assistant professor at the University of Southern California. We'll be talking about the emerging nonlinear nanophotonic platform using thin film lithium niobate. Thanks for your time today. I know it's 5 a.m. for you. The floor is all yours.
Thanks for the introduction, Alexi Zhang, and I'm very happy to be here to talk about our recent work, and then really appreciate the organizers for hosting such a wonderful event. So today I'm gonna talk about kind of a nonlinear photonic material called thin film lithium niobate, and talk about the reconfigurable aspects of this integrated photonic platforms. I think there's no doubt right now that we are living in an explosion of like data consumption, transportation, and creation. I think this is already kind of old data. So back in 3 years ago, then the total data volume that human being has been generated has already reached 40 zettabytes. So it becomes very obvious, and how can we encode data in very high bandwidth and using less energy consumption has become a central problem in the zettabyte era. And I think most of us knows that most of this data are being carried or being transported using optical signals for global connectivity. And that really brings in the advantages or why we're interested using optics and photonics, and is really compatible with the low loss, long distance communication networks. But in addition to optical communication, as we heard from the previous talk, light can also be used for efficient signal processing or even computing as well, because you can encode large amount of information using multiple degree. You can encode information in multiple degree freedoms that includes the spatial paths, temporalization, time, and frequency, and so on. And I think our integrated photonics really are offering probably the only solution that is scalable, and that you can imagine the future to integrate hundreds or even thousands optical components on a single wafer, and that simply just opens up a wide application space. And I do think the key features in future integrated photonic circuits lies in programmability, that if you have our circuits that can be reprogrammed to apply for different applications. And there are multiple challenges to solve to achieve this. I think first, of course, the first challenge will be heterogeneous integration between integrated laser with the integrated photonic circuits. And the second will be co-design between the photonic components and the electronic components. And I think the third part is really how can we build highly functional optical components, or how can we actually reprogram or route or generate this light on these photonic components. And then once that's complete, you can imagine this type of circuits can be deployed in many different application scenarios, that including sensing or LiDAR or communication in many different environments. And talking about programmability, I do think the key technology in the future integrated chips that is nonlinear photonics, because nonlinear photonics naturally allows you to control or generate, manipulate optical signals using external signals, because you simply just looking at those nonlinear interaction terms, where you like the nonlinear interaction terms give you the second order or third order, even higher order interaction terms, which naturally has this E square, E cubic terms. That means in nature, it gives you mixing between different electric field. So that means we can start to think about using an external electric field to control the optical signal. And the external field can be another optical signal, can also be electrical signal, can even be mechanical signals. Just want to elaborate on this. Let's just look at different properties and what kind of process it will enable. For example, for the Chi3 nonlinearity, which is the third order term here, that allows a process that convert two degenerate Planck photons or two Planck photons to a pair of signal and idler photons. And that you can see this process naturally gives you or generate new frequencies or new colors that is fairly close to Planck frequency. And then if you look at the Chi2 nonlinearity, that enables the process called three-way mixing, where you can convert one Planck photon to a pair of signal and idler. And that naturally gives you or bridge a large spectrum like separations. You can generate new colors that is fairly far away in terms of frequency domain from your pump. And then if you think about one of the idler photons here are down to the microwave frequency, or that can be replaced with microwave photons or even phonons. And then this process becomes an electro-optic, acousto-optic modulation process. And as you can see here, that our field is constantly driven by material science, in that we really care about different nonlinear properties and how large is the properties and where the properties appears and how can we make this property relevant to our applications. So with this, I want to talk about some of the materials I work on in recent days. It's called lithium niobate. It's was initially widely used because of surface acoustic wave filters, but nowadays it actually is also one of the most widely used photonic material as well, but largely due to its large Chi2 nonlinearities and large electro-optic coefficient. And as I mentioned in previous slides, that enables a Chi2 based process, and also a large electro-optic coefficient enables our device called the electro-optic modulator, where you can send electrical signals, and to control the light, for example, at output, you can turn it on and turn it off with external electrical signal. And indeed, if you open this kind of devices, it's about the size of a laser pointer, and if you open it, it's actually made of the crystal of lithium niobate. Okay, so in addition to these intriguing properties, there is also other excellent photonic properties, and that includes relatively high refractive index and our wide transparency window from near UV to mid-infrared, and also it also has a very large. It's also ferroelectric materials, has large piezoelectric materials, large piezoelectric response as well. So with this, I want to say that this material offers extremely flexible properties because it has both Chi2 and Chi3. It basically enables all the process I just talked about. So you can start to imagine the external control signal can be you can utilize or tailor different process to use different external control signal to control the optical light on chip. Here it's still one figure from the review paper, and really because of all the properties of lithium niobate, we can link the information or convert or unlock the electromagnetic spectrum all the way from radio frequency to hundreds of terahertz in the optical domain. We can start to think you can convert information across the wide bandwidth. So then that really kind of categorize different interactions could happen on these materials, and that will include electro-optic interaction or optical interaction and acousto-optic interaction. Though I want to say it is a very old materials, but lithium niobate has only become recently a member of integrated photonic family because of the advanced available of the thin film like materials and advancement of nanofabrication techniques. I do want to emphasize like the key of getting the optical confinement to become tighter and tighter as you go into the integrated regime really brings significant advantages. I always say, like, by making devices small, that you can also make the device perform orders of magnitude better. So there's really no trade-off here, that you get the benefits from the space and performance at the same time. And just want to give you an example. Why is that? So by really directly etching to the thin film lithium niobate, we can tightly confine the optical modes within the wavelength scale. Then that, as compared to the doped waveguides are in the bulk crystal. So the mode area can significantly reduce from like tens of micrometers to less than 1 micrometer square. And that really results in a fact that we can now think of bringing the metal electrode fairly close with respect to each other across the waveguide. And then it's just a very simple thing, because once the gaps become smaller, that means apply the same voltage, you can get significantly higher electric field, or you can think in other words that we can use significantly less voltage or energy consumptions to tune our optical signal or turn on and turn off our optical signals nowadays. And also another thing is once everything goes small, we have a lot of degree of control the properties of both optical signal and microwave signal, and that is otherwise not easy to achieve in the bulk domain. Due to the time limit, I'm only gonna introduce some of the 2 or 3 of the recent devices that we developed based on this electro-optic interaction. Before doing that, I would just want to give you a brief overview of where we are, where the state of art of electro-optic modulator is. So nowadays, we can achieve a fully integrated lithium niobate based electro-optic modulators with a switching voltage, or we call it VPI, to be CMOS compatible level down to 1.4 volts. And then you can achieve the 3 dB electro-optic bandwidth larger than 100 gigahertz. I actually think this number was updated to be 300 gigahertz nowadays. That is how fast you can encode data using the device, and with our very minimal on-chip insertion loss of less than 0.5 dB. There is a very beautiful review paper talking about different integration method, different performance of this modulator. But at very last, I do want to emphasize that the lithium niobate for electro-optic modulation does not offer the best metrics, or if you look specifically looking at one specific aspects, but it really stands out because it offers the best performance across all metrics that is relevant, and that including the insertion loss and half-wave voltage and the electro-optic bandwidth. Okay, so based on this, I want to first introduce the first device or first application that we think can make a big difference. One is building ultra-fast optical components. As we all know, like the pulse laser is a very important branch as compared to the CW laser. So it's like having a very short pulse generators can give you can have high peak powers, have like short pulse durations, so you can do nonlinear optics, enhanced light matter interaction, or starting to think probing ultra fast temporal dynamics. So, but however, to having those very short or femtosecond pulse sources on chip it's very, very challenging. It's not like we can easily take the benchtop or the large laser system and just do a magic shrink and on a single device and make it work. That involves many complex material integrations and so on. So so one of the approach we think of doing is, now we have such efficient electro-optic modulation. Is it possible that we can directly carve very short optical pulses using microwave signals? And we think answer is yes, of course. And the approach that we think of doing is called electro-optic time length. And this approach originates from the physics called space-time duality. So I think it actually originates just from the mathematical equations. So we know in the spatial domain, the light propagation is governed by diffraction equation. So that describes a phenomena that if we have a beam spot with certain beam waste, as it propagates, the beam will become bigger and bigger. And very similarly, and we have dispersion equation in the temporal domain that describe a phenomena that if we have a pulse with certain pulse duration, it will disperse to our fatter or wider pulses as it propagates. And these two equations share very, very similar mathematical expression with just a different constant coefficient in front. Also, that really means that whatever the system that we can build using our spatial imaging system, as we heard like in the previous talk, we can start to think about transferring that technology, that system into the time domain. And then let's just give you one example. We all know like a spatial lens, and what does and also mentioned in the great previous talk, like a spatial lens simply gives you, you can think about it gives you impact phase profile in the transverse domain. So if it's a concave lens, it's a quadratic phase profile in the transverse domain. And then if you think about in the time domain, that simply means if we can put a quadratic phase temporal profile onto the input temporal signals, we can build a time lens as well. And that can be implemented simply just using a phase modulator and driving with a single frequency sinusoidal wave. Because we can always approximate approximate a sine wave when it's near global minimum or near the global maximum. We can approximate this curve to be a quadratic function. Okay, so think about the simplest experiments we can do using a spatial lens is beam focusing that you can that describe a process that we can collimate. We can focus a collimated beam on the focal plane into a very, very small, tiny focus spot, spatially, right? So that means a time lens system could also enable like focusing time into a very, very short pulses, which is the ultra short pulses that we're looking for. And a typical electro-optic time lens system consists of three parts, and one is an amplitude modulator, which is similar to carving an aperture of a lens. And then, as I said, the phase modulator can act as a lens itself. And then you have to send into a dispersion median, which is mimicking the propagation distance equals to a focal length here. So here is we're able to integrate the whole system onto the thin film lithium niobate chip. And this is a closer look of the chip, where we have our one amplitude modulator and only one phase modulator, and followed by like a dispersive waveguides. Here is our experimental results. Here the experiments are still using like single mode fiber for compression, and we use 16 meter of fibers. And where you can see we can have a transfer limited pulse that has pulse duration 500 femtosecond at output. And of course, in the frequency domain, that corresponds to electro-optic frequency combs with comb light spacing equals to microwave drive. Of course, we're not satisfied with this because we want integrated dispersion medium fully on chip as well. And there is actually a very powerful technique on integrated photonics is you can do dispersion engineering by simply just tailor the cross section of your waveguide. You can largely change the dispersion profiles. Then we engineer like the cross section of the waveguide for the dispersive part, and we can design a very efficient taper to transfer the electro-optic waveguide to the dispersive waveguide. And we can achieve indeed a factor of 120 larger of dispersion value than the single mode fibers, and that really converted to the required compression length down to 0.5 meters, which is within reach or practical realization of integrated photonics. In this particular chip, so we are still kind of limited by the high scattering loss, which I don't think is fundamental. So currently this dispersive waveguide loss is 1 dB per centimeter. That really only leads us to integrated reasonably 10 centimeter long waveguide, and then we can observe a partially compressed pulse about 8 picosecond at chip output. Of course, we're not satisfied here. So we are thinking of another different dispersion management technique is to use chirp breadth grading on chip. So here shows a schematic of a chirp breadth grading, where you can see the period of this grading is linearly swept from left to right. So that really brings or phase match the forward and backward propagation wave vectors at different wavelengths. So that means this device can physically reflect different wavelengths at physically different position. And that really gives a very, very large group velocity dispersion we have measured the fabricated device and have 34,000 times larger than SM fiber. And that brings the required grading length only down to 1.6 millimeters. And we can actually make this grading loss very small, down to 0.3 dB per centimeter. Also, that really comes out of the second version of the fully integrated devices, where we have the chirp breadth grading integrated right after the electro-optic modulators, and we can observe at the chip output fully transfer limited pulses of 500 femtosecond. And I think, as I mentioned, and not just electro-optic property that is very intriguing on this material. This material also has many different nonlinear properties too. So you can start to think we can actually combining with other nonlinear properties of these materials to do more manipulation. And here is just one examples that we send our electro-optic modulator-based short pulses into another high-quality factor lithium niobate optical cavities. We can start to see this beautiful broadening of the optical spectrum up to like several hundreds of nanometer bandwidths using Chi3 nonlinearity of the material on the same material platform, basically. And another nice property I want to emphasize is the tunability or the flexibility of the operation. So we can easily tune the microwave driving frequencies to achieve our pulse sources at different repetition rate and different pulse duration as well. Here is the experimental results that we drive on the same chip, and simply just changing the RF frequency, we can get we can have different or tunable properties in both frequency and time. And of course, you can think about multiplex different wavelengths into the same chip as well. Then you can generate wavelengths multiplexed pulse sources on a single chip. I want to bring this first slide back, and if you look at the time domain. And you can also look at frequency domain. You can see there's a very nice swap between the frequency behavior and the time behavior here. That means this system not only able to compress light in temporal domain, we should able to compress light in the frequency domain as well. If you do it kind of reverse process, and that's indeed what we observed. We can compress. In this case, is in the quantum domain. We can compress the single photon bandwidth from 7 nanometers down to 0.35 nanometer bandwidth using our timeless device as well. I guess another thing I want to emphasize the reconfigurability of the device is we have talked about if you want to build a spatial lens, you put your input pulse at the global minimum, global maximum. But if you simply just adding a microwave delay or optical delay, and then you shift your optical input to the linear slope of this driving voltage or this phase profile, that we know that the frequency shift is proportional to the first derivative of phase with respect to time. So that means we can have a frequency downshift or upshift using the same device as well. And this is like experimental data that we observed. You can see a very nice kind of plot that we can tune the center wavelengths of the color of the light to like you can upshift or downshift with a very large tuning range of near terahertz. So this is an order of magnitude better than the state of art. Okay, so all this work is driven by a very ambitious program called DARPA Lumos in the United States, and I think my very last topic were related to, I think, the optical isolators. I think in almost any coherent photonic system, you will face the challenge of integration lasers with the photonic components, and that means there is a demand for optical isolators that put in between the lasers and the rest of the photonic circuits to prevent laser damage from the backward reflections. And then nonlinear optics can play a very important role in building such optical isolators, and they're indeed, electro-optic, acousto-optic, and all optical devices has been all utilized for achieve high-performance optical isolation on chip. And there's just a lot of recent development based on different techniques. But what we want to demonstrate and what we think is the most ideal optical isolator is really a very, very simple device, and that ideally, just 2 ports, you have laser input, laser output, and operation is extremely simple, but still offer very high performance of isolation. So indeed, we can actually achieve it using the thin film lithium niobate material based on electro-optic modulator, and the device is actually very, very simple. So we just need one phase modulators like this, where you have the optical waveguide that's labeled in the black line, and you have this yellow strip where you deliver your microwave signal, and then you just need to put the laser or optical light to be counter-propagating with the traveling wave microwave signal. And that when they are counter-propagating, and then you can terminate or can design the device correct that the optic sees no accumulative phase when it exits the modulator, because it sees the periodic modulation. Of course, in the design correct. And then for the backward reflection is going to co-propagating with the microwave signal. And that means the phase can be constantly accumulated as it exits the modulator. And that really creates kind of a significant phase accumulation difference between the forward direction and backward direction. You can also think about the modulation efficiency becomes quite different. And then if you just work out actually very simple math for how a phase modulator works, you can see if you can achieve a specific operation point of modulation index, is possible to completely deplete your pump. Or if you're driving at 0.765 VPi, and so that means you can have a very ideally theoretically infinite optical isolation at a pump frequency. And that's indeed what we see, where you can see here we can achieve more than 48 dB optical isolations at laser frequency. But I do want to emphasize, like, the light doesn't just disappear or get attenuated. It's actually based on this non-reciprocal spatial temporal modulation. The light is being redistributed over other frequencies, but just not at the pump frequency. So that means we can easily, for the backward reflection, we can easily filter out these new colors using a reciprocal device, for example, a ring-based filter, right? And we actually monitor our isolation performance, and we see with like only 0.1% of microwave power fluctuation can still maintain optical intensity fluctuation can still maintain the optical isolation about 40 dB. And also this device can constantly and stably operate over many, many hours and still offers very high performance. And since our device is a simple waveguide geometry-based structure, it can actually operate a very wide optical broadband bandwidth as well. And we actually proved our isolator can interfacing with an integrated laser and protect the single mode operation of the laser as well. So we actually test our devices with hybrid integration method with the laser. Okay, so with this, I want to kind of summarize my talk. I have talked about the spectral and temporal control of our optical signal using microwave signal. And I have talked about electro-optic high-performance optical isolators based on programmable electro-optic materials. And of course, I think the aspects of lithium niobate is not just electro-optic devices. There are many other, I think, many other exciting devices you can build. As I said before, you can use optical and even mechanical signals to control. I want to bring this back, and there's very nice materials can link a wide range of electromagnetic frequencies. And then we actually write a review that is published in Science, like beginning of the year, that we kind of predict where this material is going to play a role in near term, midterm, or in the long term. We could be very wrong here, but we do think this platform is going to play or going to make a difference in many aspects, including data comps or AI or even quantum computing in the long run. So with this, I want to thank many of the work is actually done during my postdoc period at Harvard, thank my previous team and my advisor, and I'm currently leading my own group at USC, and this is my group members and funding agencies. And very, very, very last, I think, the reason we're all here is because we are, I think many of the audience are young scientists, or like I mean, the kind of experience I learned in the past is like growing a community and building a community and making the community better. It's very important. So if you have any questions regarding to science or professional development, I leave my contact up here. So with this, I think I want to thank you for your attending or listening to the talk. I will answer your questions at the end.
Thank you very much, Mengjie, for your interesting and very inspiring talk today. Moving on to our next speaker. So our final speaker is Haoran Ren. He is an Australian Research Council DECRA Fellow at the School of Physics and Astronomy at Monash University. Today he will be talking about 3D metafibre optics. Please welcome Haoran, and the stage is all yours.
Thank you very much, Sejong, for the introduction. Let me just share my screen. Can you see my screen, Sejong?
Yes, we can see. Yep, all good.
Yeah, thank you very much for turning up. So either to be very late or the very early, especially for Mengjie, for instance, and also for the people from Asia, it's getting late. But yeah, thanks for staying with the talk. So we already witnessed, many beautiful examples from Inki and from Mengjie for their nanophotonic platforms. In the next half hour, I would like to just to introduce our recent work in metal optics, which we put the metal surfaces on top of the fiber. So just to drag your attention slightly back to the metal surfaces that Inki has introduced quite a lot. But hopefully you will find it useful why we have the motivation to develop the metal surface in 3D, and why it's useful. This platform can be used to functionalize the optical fibers. So I'm going to cover, some design principles and the nanofabrication based on the laser writing for the metal surface printing, as well as the applications for some fiber optics. Yeah, so just give a very quick introduction again, going back to the metal surface, even though, the Inki has already shown many beautiful examples for this. Just for the audience, those of you, not in the field of metal optics, so we are talking about metal surfaces with the thickness, could be 2 orders of magnitude thinner than a human hair, right? So this is the very thin and ultra thin device. even though the thickness is very thin, but XY dimension transverse size, you can just spread it out, all the structures in the large scale, so that which means using the different nanofabrication platforms nowadays, you can make the metasurfaces really in the commercial scale. So it's a really useful device. And the vision is to use the nanostructures that they harness the strong light matter interactions for the light manipulation, right? So consider, for instance, if I can just bring my pointer here, for instance, if you can think of the nanostructures that they have a strong light matter interactions, they can host the optical modes or the resonance, you can change their size, their shape, their orientation, whatever. So in the local field, they have a very strong light matter interactions, so that the scattered light can be re-emitted based on the property of this structure, which is controlled by their physical dimensions. For instance, in this case, putting them together with the wavelengths not that very small, but it's still sub-wavelength, so that you can control the outgoing wavefront, even though the shining the light with the normal instance, for instance, but the outgoing wavefront can be arbitrarily controlled. So today I'm going to present a few examples that from our recent efforts. We've been working on the 3D metal optics and putting this kind of structures on top of the fiber, and especially just wanted to convince you, why we use the 3D laser printing for this kind of devices. And apart from the technical side, would like to just introduce, some physically interesting points why we need the 3D metasurfaces. And this is the commercial device that we used to print out metasurfaces, which is called Nanoscribe from Germany. It's a very successful spin-off company based on the 3D laser printing. So just to give you another example slide, for the audience who are interested in the metasurfaces, recently we also contributed a review article where we showcase many metasurface examples with the focus particular in the energy conversion. It's not in the wavefront control, but still you can think of metasurfaces you can make into like a single nano antenna, and then they have to, they don't have to very much close to each other. They can be far apart, but they have a strong light matter interactions that you can think of the applications like energy conversion, or you can think of the 1D chain, 2D array, or even stacking the metasurface in 3D based on the different metal atom design. The metal atom is actually the single unit cell of these structures, right? And in terms of this wavefront control, we also, we have summarized some examples of the metasurface that have been popularly used in the state of the art. For instance, the Huygens metasurface, dielectric metasurface, based on the truncated waveguide, or anisotropic waveguide metasurface, where you can reach the geometric metasurface response. So if you're interested, please just visit our review article. But today, this is just giving some general introduction or the background of this field of the topic that I'm going to present. But today, would like to just introduce a bit more on the 3D metal optics, and with the two particular examples that I'm going to show. The first one is called achromatic metafibre, and the second one, very recently, we put this metasurface on top of the fiber, and we transform the single mode fiber into arbitrary structure-like modes, right? So our vision is not using the fiber to develop the modes or support the transmission of this particular modes, which like a single mode waveguide, which is usually challenging. So our vision is, instead of supporting such mode for the low loss propagation, but we transform on top of the fiber, just also can be delivered to the users, if they're interested in the use of the structured light for some applications. So I'm going to showcase some designs and the printing, and of course the characterization of this kind of metal fibers. Instead of scaring you for this slide, but just showing you, what's the major difference between the 3D metal optics that I'm talking about. and versus, you know, the state-of-art metasurfaces that usually based on the planar lithography. So as you can see here, so basically in the top and the middle part, that's a lot more metasurface examples. But if you look at the structures, not what, you know, it doesn't matter they rely on the resonance-based metasurface or it's you know, the broadband geometric metasurface. So basically they are planar structures, right? It's an ultra-thin device, of course, but it's based on this fabrication approach. You know, you have to do some etching for some cases, and you end up the metasurface with the single height. So what we mean by the 3D metasurface, based on the laser printing, basically you can define the structures really in the 3D. And this can give you, you know, basically unleashed high degree of freedom. So basically we can control the metasurface in the third dimension, which is the height. Not possible if you work with the planar lithography approach. And also this platform allow us to put the metasurface on the flexible substrates, including optical fibers. And not only for the wavefront control, but also, you know, the 3D structures can be used to enhance light-matter interactions, creating this high quality factor metasurfaces as well. So this slide just to summarize, you know, what's the unique features of the 3D meta optics. First of all, as I mentioned, you know, that offers the higher degree of freedom, which is not usually available, right, in the metasurface community. And also you can stack in the multi-layer metasurface easily using the laser to print in multi-layers. And imagine that if you have like every single layer, you have an individual function, then basically this function can be stacked up, right? So the third one that, you know, you based on the laser without etching, without the electron beam lithography approach, you know, you just put in the photoresist on your sample and using the laser to create like a point source to create these structures. And then you basically, after the development, the metasurface is done. So it's a fairly easy approach, single step. So the journey begins from the Satoshi Kabata's group, basically in 1997. So they developed this kind of, for the first time, two photon polymerization approach, where they use the laser as the pencil inside this photoresist, for instance, also going through some nonlinear process, as Mengjie has introduced this process, but we're not going to talk too much about this. But just let you know that two photon polarization is obviously it's a nonlinear process. Instead of absorbing the single photon, but simultaneously absorbing two photons altogether, so that you can imagine the impulse function of this focal spot or the PSF could be smaller based on this second order, you know, nonlinear effect. But the major player of this two photon polymerization is also the threshold effect. Basically, you study this light matter interactions. Creating these beautiful 3D structures, you also need this spot to be smaller, like a laser pencil. So in order to make this smaller, basically we can think of this kind of a polymerization threshold, right? The material has the response. Once it's reached the strong energy dose for the photon energy, so that this part can be polymerized. Otherwise, you know, this could be washed out during the chemical development process, so that you end up with the structures from the very tiny PSF centralized the spot area, so that can basically define the resolution of this 3D laser nanoprinting, which is about 300 nanometer in the transverse direction, and also about 1 micron in the longitudinal direction, without playing many other games. So this is the one of the examples that why we need the 3D metasurfaces. This is just to show you the example, like if you can fully release the high degree of freedom. So this kind of dimension that can be used to control not only the phase, but also the amplitude, as Inki has introduced many examples of the metasurfaces, right? The metasurface holograms. So when you develop the hologram, you know, every time you do the Fourier transform process is always based on the complex amplitude. So even though we use the phase as the approximation for this field, but if you can directly create this complex amplitude modulation, that would be perfect, right? So that would be perfect platform. So the 3D metasurfaces as the example here, we use the polymer nanopillar structures, we use the height degree of freedom to control the amplitude response, and we make the structures to be anisotropic, like this truncated waveguide pillar, right? And then the XY directions, based on the rotation phase, basically we can control the geometric phase response by creating this, the optical response along the short axis and the long axis of the polymer pillar to be different with the pi phase difference, so that you can simply rotate them and create this phase response. And the height defines the amplitude. Altogether, you get this 64 levels of complex amplitude modulation. But just to be clear that in order to have this kind of a response, we have to make this low index polymer pillar to be very tall. So the aspect ratio of the structure is really high, right? This is this is the tail down the structures that are putting into the surface, that just showing case how tall these structures are. This is the difference from the conventional high index based metasurface, where you still have a high aspect ratio, but not like this high. Okay, and another example, just saying that you can use this kind of metasurfaces not only for the wavefront manipulation, controlling amplitude and phase, even polarization in the next slide I'm going to show you, but also you can create this 3D nanofilm metasurfaces, or whatever you want to call, but that harness the strong light-matter interactions with the resonance called the bond states in the continuum, so that you can break the symmetry with this 3D structures by changing the incident angle, or even nicely you can just define using the laser these 3D structures with like a triangle shape. So the opening angle of this triangle basically can introduce this asymmetric factor, right? So basically you can reach this symmetry protected bond states in continuum. So this is our fabricated structures that we coated with gold to achieve this plasmonic bond states in the continuum response. But today, going to focus a little bit more on the achromatic metafibre as well as the structured metafibre. Due to the time limit, I would like to just go through the design principles quickly, because the paper has already published, but just restate a little bit more. So the reason that we would like to control the chromatic aberration is very obvious, which is, different colors, like Mengjie's example in the waveguide, even, they have a dispersion, right? The lens structure also has a dispersion, which means if you're shining the broadband light for the single lens structure, these different colors can never be focused down to the single spot. They will be shifted away. So this is the normal dispersion of this bulky lens. But in order to compensate this conventional way, first, the lens is already bulky, very thick. But in order to compensate that, you have to play around the multiple pieces of this single lens, so making the device even bulkier, right? So it's not ideal. So for the metal lens, obviously you have like opposite dispersion approach, which means, for instance, like if we is using the geometric phase, for instance, to design the metasurface, so you're shining the red color, this is the nominal wavelength that you design the lens. Now, if you switch to the higher frequency according to the lens function, that you need this more stronger banded this wavefront in order to form the same focus as the red color. But unfortunately, for instance, based on the geometric phase, this phase profile is constant, right? Even you shift the wavelength, so that this is the realistically you offered this wavefront, so that it's like more flat, so that push this wavelength away from the focus. If you're shining higher frequency, then push more from the metasurface. So this is the dispersion that has been identified. But just showing that why we're interested in the 3D meta optics. So this is the kappa is defined as the time bandwidth product of your metal lens in order to have a broadband coverage, right? So this is based on the height time. So basically like the phase response that you can offer from the structure with the maximal refract index, effective refract index, and the minimal refract index, particularly like the truncated waveguide type of metasurface. So if you have the single height, basically the only thing that you can play around is effective mode index of your truncated pillar. But now if we release the degree of freedom of the height, as you can see here, simple derivation of this equation, you can make the kappa to be larger. Basically, you can work with the maximal height of the pillar with maximal effective mode index and minus this minimal height times this minimal effective mode index. So that can basically extend or expand this group delay response so that you can coverage more different wavelengths. Just a showing case, like 2D case, people have to play around these structures with different shape in order to create different effective mode index. So we use this very simple structure, which is like a 3D nanopillar. Again, it's a single nanopillar. But this time, it's not amplitude modulation, but we are interested in the group delay. So with the J from the Johnsack-Ross group from the PostTech, which is also the same as the Inki's previous group. So we developed this achromatic metal lens, basically based on this phase profile together with the group delay. So for this achromatic lens, not only the phase profile form the focus, as I mentioned, you also need to control the dispersion, which is called the group delay. So altogether with this two response, basically you can achieve this achromatic focus. The second example, just quickly go through with our recent work, basically, again, based on the single nanopillar in the 3D. So why we always stick with this simple 3D nanostructure, not a simple 3D structure, but just a very simple 3D pillar, right? The reason is, of course, simpler, better. It's always like you can say what is the maximal you can get from the simplest physical system. So for this, nanopillar, again, based on some simple math, based on Jones matrix, by shining the light with the linear polarization as the input along the x direction, for instance, and you do some derivative of this Jones matrix, you get this response for this pillar with the rotation angle of gamma, for instance, here. And then you can get arrived at this equation, basically not going through that too much detail, but just would like to draw your attention here. It indicates that we can control independently. Possibly, we can offer this equation offer us this possibility, right? So we can control the phase and the polarization response down to the single pixel level, which is the nanopillar, so that you can reach this independent amplitude and independent phase and polarization control. Suppose amplitude is maximized as always, right? So this gives us this opportunity that we can get arrived at this 3D metal atom library, which based on the 3D nanopillar structures with this height dimension, as you can see, that I just would like to emphasize here, like traditional metal surface, if it's a single layer, you only have like this metal atom library with this kind of one layer structure, right? So, but if we just make this like a degree of freedom, so basically you can get like a metal atom library, which is like a volume-based metal atom library, so that you can select the structures with a very broad range, basically. So the idea that we use this kind of broad phase coverage and phase difference coverage for the polarization control and the phase, for the propagation phase control, which is the polarization and the phase independent control. So we wanted to realize arbitrary structured light, which can be generalized on the hybrid order Poincare sphere. So based on the superposition of the left-handed and the right-handed circular polarization with different orbital angular momentum modes and with the different phase and amplitude components. So that all these states that can be generalized on this Poincare sphere, as you can see that with different states you get a different specially invariant optical beams, which means the polarization is actually not like a homogeneous. The polarization is spatially dependent, right? So you can get this linear dependent like a radial and azimuthal polarization or circular polarization carrying optical angular momentum modes on the south and the north poles, basically. But if you can go to the arbitrary states, which is like most general case that carries the elliptical polarization with the different orientations as an example. Okay, so now let's have a look about the structures that we have been working on. So this is the first example that I would like to show you. Is on top of the SMF 28 commercial single mode fiber that we've been used for our fiber communication, telecommunication every day, right? So on top of this fiber end phase, we directly put this tower structure to allow the beam, the fiber output, because it's a single mode, so allow this beam to be diverged and to a certain size and reach the metal surface where we put achromatic metal lens on top, right? And this is the performance of this achromatic metal fiber from its single mode region. So basically that covers from 1250 to 1650, that's the whole single mode operation range. As you can see, if you use our achromatic metal fiber, basically you can get this focus more or less the same position. Well, if we just try it without doing any chromatic aberration control, we just put this standard metal lens with the lens profile, as you can see that with this NA of 0.2, basically you can shift the focus quite dramatically, right? Which is not ideal for applications. For instance, working with Chen Hao, the PhD student at LMU Munich. So basically, we shining the broadband light on this image target. We didn't have this endoscope catheter, which allow you the scanning the fiber directly on top of the fiber. We didn't have that, but we just scan the stage just to make sure it's clear. So this is based on the image object. The image itself is scanning, but so the device that we did this kind of confocal imaging is just this single fiber between the image and the photo detector, right? So the in between there's no any optics. So this is the most beautiful things that you can think of. Basically can squeeze your optical system between your target image and your detector, just a fiber, right? This is the ideal case. So what we achieved here, we use our achromatic metal fiber with different wavelengths. As you can see that we get more or less homogeneous image response. But if you switch again back to the normal metal lens fiber, basically, the intensity and also the resolution that sacrificed quite a lot based on the different wavelengths, because that lens was designed for this particular nominal wavelength at 1650. Right. So, and a couple of examples to finish my talk. So basically, as I mentioned, we can create this arbitrary polarization in terms of the radial and azimuthal polarization on fiber, as well as this, circular polarization carries different orbital angular momentum modes, that -1, -3 on fiber, as well as we just pushed our design basically into the arbitrary form. So basically, you can reach arbitrary structure that on top of fiber. So again, the vision is instead of having the particular optical modes, basically we can transform that mode directly on fiber and deliver to our user, right? So if I can, this brings me to my summary slide. So I hopefully have convinced you at least the 3D metal fiber could be platform, or the 3D metal optics could be the platform that has the unleashed high degree of freedom that can offer you not only technical advantage, but also physically advanced light control for the amplitude, phase, polarization, dispersion, so on and so forth. And also you can imagine the stacking the metal surface in multiple layers using the laser, which is fairly straightforward to do. And of course, it's a faster and cost-effective single-step process. With that, I would like to give the credit to my colleagues and the collaborators, from Germany, from the Korea, and also Stefan Meyer, who has recently relocated to our school at Monash University. And yeah, so if you're interested in our research, feel free to visit our web page or whatever. Yeah, I'm ready for questions. Thank you so much for your attention.
Thank you, Haoran. Thank you very much for your very interesting talk. Next is our panel discussion session. I'd like to invite everyone to our virtual stage here. Yes, I see everyone there. Again, I would like to express my gratitude to all three speakers today for taking the time to present their exciting research findings. And also, I'd like to mention that all three speakers are across the globe today. So Mengjie from US and Inki from Korea, Haoran from Australia, and we're all in a different time zone. Also, as someone who is at an early stage in my own career, I fully appreciate your immense effort and dedication for your research. And I'd like to take this opportunity to express my appreciation. So this panel discussion is why I like the ICANX talk, because this is different from conventional conference Q&A session, because we are also allowed to ask questions to each other. So I guess I will also see if I have questions from our chat box. So audience, you can share your questions that will be delivered to me. Otherwise, maybe I can start asking questions to one by one. Maybe I can start from Haoran's talk. It was really interesting. It was actually the third time that I hear your talk. Every time I see your presentation slide, you always have something new, which is very exciting. So you talked a lot about 3D structures on a fiber and advantages that are following using 3D structures. But I also want to hear what would be some challenges. For example, I guess fabrication time or anything. Yeah, I'd like to hear from you.
Yeah, absolutely, Sejong. First of all, thank you so much for chairing this session. Yes, I hope I didn't discourage you. You mentioned 3 times. Yes. In terms of the fabrication on the fiber, yes, that's right. So the 3D laser printing, I think, as at least from my personal perspective, you are right. The speed is one of the most challenging issue. One of the challenging issues actually, because this is based on a highly sequential process, right? It's not a nano imprinting. I think Inki has a much more good perspective than me in terms of this metasurface fabrication. In terms of this, their group can do really large scale nano imprinting approach. But the laser writer, yes, of course, it's based on a single laser point, right? So you basically write these structures inside the polymer, which is fairly slow. Even though the people developed some method, but still this is the far from the commercialization, at least from my perspective. The secondly, in terms of metasurface with this particular angle using the laser to print, it's the index, because the polymer obviously has a much lower index as compared to, for instance, silicon or silicon nitride, the gallium phosphide, gallium nitride, all these high index transparent materials in dielectrics, so that this index low, in order to form some photonic function, sometimes it's painful. So for instance, our pillar, as I mentioned, you have to make this really, really tall in order to have this kind of certain optical response. So yeah, so hope with these 2 points that I answered your question.
Right. I also had a question regarding the low index polymer, because you already mentioned that's the disadvantage. Is there any way that you can kind of go around these issues, or is there any technology that you can use 3D laser printing but still for higher refractive index?
Yeah, Sejal, thanks. So directly forming this polymerization process, as far as I understand, it probably is challenging, but you can work with different material platform. For instance, people using the laser to write inside the graphene or other high index material, but of course, it's not based on this growth of the structure. Polymer, you can grow the structure in 3D in arbitrary form. But for the other material platforms, most of the people basically just to either introduce the local refract index change that you cannot really define the structure. You can define a 3D index profile, refract index profile, or you basically using the laser as like a kind of a
such a wonderful moderator, and then two speakers. I feel I learned so much. I'm gonna teach Metasurface. I quickly learn it and teach Metasurface in the class later today. But before that, I do want to ask a general question. Was wondering, I mean, there is fantastic performance from the meta lens, like both of you have presented. Was wondering, what are remaining I mean, are we really at a time that we can say we can replace the conventional lens with the meta lens nowadays, with all the aberration correction techniques or managed dispersion, 3D even? So are we close, or how close, or how far, and what are the remaining challenges? I guess that's to both of them, like both Inki and Haoran. Yeah.
Yeah, Inki, you go first. I think you have a much better perspective on this.
So I think still we need many hurdles to replace conventional optics, indeed. But the biggest advantages of Metasurface, in my opinion, it's multifunctionality. Multifunctionality for specific application. So like a land imaging or holographic display and so on. So in my talk, I introduced holography display and imaging technologies. But these days, I've been using meta lens for specific bioimaging. So for instance, it can work simply general mode imaging, but also it can be used for edginess mode. So for a specific application like such biocell imaging, then it will be quite useful, I guess. But still, it's quite difficult to catch up conventional objective, I guess.
Yeah, so if I can just add a little bit more perspective on this. So as the Inki said, yes, we have a challenging, but we also aware that the industry is starting to pick up these fields, right? So from the US, like Harvard Group, Capassos Group, and they have a spin-off company, and many others around the country and also across the world. I think there's more and more people like Inki presented Samsung, right? So they made the example of AR, VR, all these kind of things, the LiDAR, all these things, face recognition using the flat optics. So for the multifunctional, I think, yes, indeed, very challenging. But I just start to feel that from the recent years, the people already can commercialize some of these simple functions. For instance, if you only need the lens, simple lens structure, right, on the phone or whatever. So this kind of things seems like already happening.
Thanks. Yeah, thanks for the answers. Yeah.
Maybe I want to ask more on that. I really like Mengjie's question, because that's the same question I had in my mind. Because when we hear about metaphotonics, people talk a lot about like you can reduce the thickness of your lens. So let's say the bulk lens is 1 centimeter and the meta lens is less than a millimeter. Could you give us some example where you see this is big advantage in like which applications, for example?
Inki, you want to go?
Yeah. So I think maybe let's say if we are using Haoran's like a metafibre then maybe it can be used for endoscope, isn't it?
Absolutely, yeah.
Yeah, then endoscope, it has a quite bulky optical system as well. So let's say if it goes into our body, then it will be more comfortable compared to the conventional one. Then it will be interesting.
Yeah, definitely. Also, like this kind of a lens, right?
Right,
It's a
right. From camera, right? Exactly. Right.
Yeah.
Thanks for your answers. Maybe we can also ask questions to Mengjie's presentation today was about lithium niobate. I know you're one of the leading group that's actually leading this research field. It was very interesting. I also really like the first few slides where you tailor down why we're doing photonics and where this integrate photonics go, and why we need nonlinear material. And I also remember the part where you said the research area is constantly driven by material engineers, which is, I fully agree. In that regard, because also you wrote a review paper on that, is there another emerging material other than lithium niobate? That was my question.
Yeah, I think definitely. I think yeah, so I mean, like, of course, I think in every field, right, that we're doing. I mean, we're not material scientists, but always very excited when there's materials with intriguing properties pops up. I think closely related to your question, I think BTO has attracted many attentions, like in recent years, and I think groups from like IBM Zurich has like developed very nice BTO thin film. I mean, all these breakthroughs on lithium niobate all comes from the availability of growing good quality thin, like thin film, right? So I think we'll see a similar trend for thin film BTO as well. And BTO is a very nice material, nice electro-optic materials, and then it has the electro-optic coefficient is, I think, more than 100 times larger than lithium niobate. So it's gonna make I think you're gonna see it making a lot of waves in the future, and also materials that can have memory. I think is getting tractions as well. So I think there's no doubt that it's very hard to have memory in optics. Now optics travels very, very fast, and then unlike electronics, we can have many memory devices, but photonics is very hard, and it's also we need to see more progress in terms of discovering, like, for example, phase change materials or ferroelectric materials. Both of them can have can store information in a non like volatile way, so you don't need to consume any energy, that you can store information in those materials. I think those three are probably most exciting. Well, the BTO actually is a ferroelectric material as well, so I think it kind of has space in both in both spaces. Yeah, we actually also working on exploring some new materials in my lab. So,
all right, yeah. Thanks for sharing that. On that regard, can you also so you mentioned memory, and you also talked about modulators and isolators. Do you see, because in the beginning of your talk you talked about all the optical components for programmable integrated photonics, is there some components that you think is missing or that needs more push to make everything available?
Yeah, I think, as I mentioned, I think the three challenges still remains. One is heterogeneous integration between active and passive photonics. I mean, each of the field making like excellent progress by integrating or interfacing different materials, no matter on the front end, on back end, or hybrid or heterogeneous integration. They're both very challenging. And then the second is the co-design between electronic and photonic devices. How do we interfacing with especially very high-speed electronics, high-speed ADC, DAC, and they're fairly small, right? And they're based on most advanced CMOS technology. How do we interface with the orders of magnitude larger photonic devices? And I think the third is the materials, highly functional optical components as well. I mean, we talk about metasurface, but it's also in-plane photonics. We also want multifunctionality. So, but I still think probably we need to see more progress in the photonic memory devices. Yeah, currently they're still very lossy. Well, they can give you a large index change, but at the same time, it also gives you a change of absorption. It's something if that was solved, I think it's going to make a big deal in terms of reprogrammability. Because every time, if you want to reprogram for certain applications, you don't need to reprogram many times, right? Or it's probably like a very low frequency kind of change. So if this kind of reprogrammability doesn't consume energy, I think is a big deal.
Thanks for sharing your perspective. And Haoran, Inki, would you like to ask a question to Mengjie?
Yeah, I have a question to Mengjie actually about efficiency, because the nonlinear process it's usually very low efficient, right? I'm just wondering now how efficient by putting these things on top of the chip from your perspective.
Yes, so I think efficiency is always a big problem since the invention of nonlinear optics, and I think it's also one of the driving forces why people want to do nanophotonic nonlinear optics. The reason is we can drastically enhance the efficiency. So I will say with very so I will say for the process I listed, for example, Chi3, Chi2. And in electro-optics, you can achieve near unity conversion efficiencies with very moderate power. That on chips, either optics or microwave. I mean, we have demonstrated like 100% conversion efficiency using like 100 milliwatts, 100 milliwatts microwave power, which is already significant. For on chip, I mean, you already for the Chi2 or Chi3, you already see using like milliwatts or microwatts of level. You can see very efficient process. And I will say acousto optics is a little bit hard. So achieving near unity conversion efficiency using mechanical wave driven, it's very challenging. I don't think anybody has achieved using a non-resonant structure. Yeah, because we always care about non-resonant, right? I mean, the non-resonant structure gives us our metric or standard to measure how efficient the process could be. Because you can always use resonant structure by reduced bandwidth to enhance the efficiency. But the key, the sign, if you can do this in a waveguide structure or non-resonant structure, that I think can be a common standard to measure the efficiency. I think acousto optics is still a little bit behind, but still, I think you have to use nanophotonic or nanostructural engineering to achieve high efficiency in the future. I think that's no doubt on that. Yeah.
Cool. Thank you.
So I have a first question, Mengjie. So I'm curious whether your integrated photonic device can be coupled into the free space optics as well.
Yeah, I guess define our free space optics. I do think it's an interesting kind of topic, whether you can use, for example, matter surface to steer light to decide which waveguide you're coupling into, right? I think it's interesting, especially in the context. I mean, nowadays I'm doing optical computing as well, so I think it's in the context of optical computing. It's very, very interesting because our spatial degree of freedom can give you a very powerful capability of multiplexing, and combining with on-chip temporal scaling too, I think will be very powerful. We're looking into how can we using some free space components and then direct light into different waveguides. I think in principle, based on calculations, possible. I haven't seen too much research on this, to be honest. Yeah.
Thank you.
Yeah. Actually, the metasurface on waveguide is emerging, right? As far as I remember, there's a couple of groups that are working on this. They put in this like metasurface, like a dress up on top of the waveguide, so you can control the mode conversion inside the waveguide. You can couple the free space into the waveguide, or vice versa, waveguide mode and couple to free space. But yes, as you see, it's only emerging. But I think very interesting could be combining these two fields together.
Yeah. I think like auto and LiDAR and also like addressing trap ions is some people do that because the ions has to be on top of the photonic structure and they want to deliver their UV beam on the ions. They also want to collect the emission like photons from the ions as well, or back to the integrated structure. So, and I do think maybe is it Capasso also have an interesting kind of demonstration. He used probably also nanoscribe to print a lens. I don't know, like on the tip of the waveguides and focus.
Nanfeng Yu and and Xinjie also they work on this kind of a system recently, as far as I know. Yeah, and many others, of course.
Yeah.
Right, thanks for that. And maybe we can move on to Inki's talk. And because his talk was the first one, I'd like to just remind with some of the keyword I wrote down here. So Inki today talked about many interesting applications using metasurfaces. So it was about dual mode hologram. And he also talked about active metaphotonics using liquid crystals. And I remember some very cool videos showing all the applications and holograms. He also talked about vectorial holograms. So maybe these keywords will help Haoran and Mengjie to remind what he talked about today. Maybe I can start question. Very simple question. It was really interesting that Canadian dollar had a hologram, which I didn't know until now. So what's the hologram embedded in this note?
I didn't look it carefully, but it was just number images. But I think it is made of some polymer, it's like a diffractive optical element, I guess. So you can make some polymer pattern inside the field. Then you can generate a holographic pattern, I guess.
And you also talked about holographic sensor for a gas sensor. So I wasn't sure if you mentioned cheaper than the competing technology, right?
Yeah, I guess so, because if we are considering the nano imprinting method, then it's like continuous manufacturing. Then maybe hopefully we can make it cheaper compared to conventional one.
Right, and also I had a question regarding the mechanism of this sensor. So you have liquid crystal, and if you have volatile gas, and if the gas is absorbed, the liquid crystal state will change. And I wasn't. Could you explain more about why the liquid crystal changed?
So, gases, it just break the order of liquid crystal, ordering of liquid crystal. So first, because of the microwell grid structure, the liquid crystal orientation is well aligned. But once the gas is coming, then the ordering will be changed. So if you shine the light, then polarization state also will be changed, and it makes hologram pattern changes.
Thank you for your answer. For the interest of the time, I'd like to have a quick question from one of you or both of you.
Yeah, can I ask a question? So Inki, how fast your switching speed was?
It is in millisecond.
The liquid
crystal. Yeah.
Okay, cool. And how small the pixel is?
Pixel is 1 micron, I guess.
Okay. In 2 dimension.
Yeah, right.
Cool, thanks.
Yeah, I also have a question. I think I was very impressed. So I was wondering, for the liquid I think people always want to do dynamically tunable or metasurface. Or I was wondering, is the demonstration, is it pixel by pixel tunable, or is actually apply a constant voltage across the plane?
So here we didn't make a liquid crystal pixel because it was very difficult to change pixel by pixel. We need very complicated electronics. So rather than we just use simple large area liquid crystal. So we are just changing the outgoing polarization state, and on top of the liquid crystal we have metasurfaces. So the metasurface can do something based on this outgoing polarization state.
Okay. But ideally, you want to have the pixel by pixel tunability, right?
That is future tunable.
So what's the challenging here? Is it just like very hard to? Is it purely on electronics, like very hard to control 1,000? Like
I guess so. In the school, it is very difficult to fabricate those kind of liquid crystal pixel array. So, but the company, they can do it easily, like display company. So, but we didn't have any chance to collaborate with company. So we are simply using.
Right, that's what I thought too. The display already can control a pixel by pixel, right? So does it mean actually this challenge already solved? Like you can actually already have a
maybe right.
Okay.
They already consider this technique.
Okay, thank you everyone again. I'd like to wrap up our panel discussion session, and thanks again. Let's see if I can see the next slide. So to show our appreciation, we'd like to give you a certificate. It will be sent to your email. Again, thank you, Inki Kim from Sungkyunkwan University, and Mengjie Yu and Haoran Ren. I hope I can see you in person sometime this year. Also, we have another youth talk next week, so make sure that you're not missing the talk next week. And with that, I'd like to wrap up our session today. Thanks again, everyone, speakers, and also Elise. Thanks again for hosting this amazing session.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想， 希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。像我一样飞越